Good day everyone. Welcome to all. My name is Sachin Ahankari, working as Assistant Professor in Narasimha Reddy Engineering College in ECE department. So today in this session we will see about the AC characteristics of op-amp. So there are three types of AC characteristics. The first is slew rate, the second one is the frequency response, and the third one is power supply rejection ratio. So slew rate is defined as maximum rate of change of output voltage per unit time. So here the slew rate is going to occur due to the internal capacitance or due to the external capacitance attached to the op-amp. So the capacitor within the op-amp is generally used to prevent the oscillation, and this capacitor is having the disadvantage that it prevents the output voltage from responding immediately to the fast changing input. If the fast changing input is applied to the op-amp due to the capacitance present inside the op-amp, it will not respond to the fast changing input. So this happens because the capacitor has the property that it will take some time to charge, and it will take some time to discharge, and due to this property it will not respond instantaneously to the fast changing inputs. Let us consider that the op-amp is connected in voltage follower configuration, and in the voltage follower configuration the output voltage is given to the inverting input terminal, and to the non-inverting input terminal we are attaching the input voltage. Let us consider that square wave is applied here, and negative feedback is used here. So here, if the slew rate, uh, so whenever I am applying the square wave here at the input of op-amp, I am expecting the same square wave at the output of op-amp, because op-amp is connected in voltage follower configuration. So output voltage is equal to the input voltage. So I am expecting the same wave, but due to slew rate, if the slew rate is let us consider the slew rate as 2 volt per microsecond. So I am taking this 0 to 5 volt, and the time period for positive duration of square wave is 5 microsecond, and for negative duration is 5 microsecond. So 5 microsecond and 5 microsecond here, and total time period is of 10 microsecond. If the slew rate is of 2 volt per microsecond, so after 1 microsecond it will attain 2 volt. Again after 1 microsecond it will attain 2 volt, and after 0.5 microsecond it will attain 1 volt. So approximately 2.5 microsecond it will attain the uh, maximum value of the square wave. So it will take 2.5 microsecond to reach at the 5 volt. Again it will take 2.5 microsecond to reach here, and it is going to produce the trapezoidal type of wave instead of square wave. And if I am again going to reduce the slew rate from 2 volt per microsecond to 1 volt per microsecond, then at that time here for 1 microsecond it will go for 1 volt, for 1 microsecond it will go for 2 volt, for 5 microsecond it will go for 5 volt, and it will produce the triangular wave. So here if the slew rate is reduced, your output voltage is going to be distorted. And if you increase the slew rate, let us consider the slew rate as 5 volt per microsecond. So during 1 microsecond it will attain the 5 volt. Again here it will go back here to that value within 1 microsecond. So approximately same square wave will appear if you are going to increase the slew rate. So ideally the slew rate is infinite. Ideally it should be infinite, and as the slew rate is going to increase, if the slew rate is high, you can use the op-amp in high frequency applications. If the slew rate is low, you cannot use the op-amp in high frequency applications. Here, if you go for the uh, if you go for the uh, derivation part, instead of a square wave, let us consider that I am applying the sinusoidal wave Vp sine omega t. If I am applying Vp sine omega t, I am expecting Vp sine omega t at the output. So here the output voltage is Vp sine omega t. So the definition is maximum rate of change of output voltage uh, uh, per unit time. So here the output voltage expected is Vp sine omega t, and d dt of V out is equal to, so here rate of change of output voltage is equal to rate of change of output voltage is nothing but derivative of this with respect to t. So here the derivative part, Vp is constant, Vp is taken as it is, and the derivative of sine omega t is omega cos omega t. So I am expecting the maximum rate of change. So for maximum V out, the maximum value of cos is 1. So here maximum value of cos is 1, therefore maximum rate of change of output voltage is omega Vp. So slew rate is omega Vp, since maximum value is 1 here. So slew rate is omega Vp. Omega is nothing but 2 pi f. So 2 pi f Vp. And if you are interested to calculate the slew rate in volt per microsecond, then at that time 2 pi Vp f divided by 10 to the power 6 volt per microsecond. So you can calculate the slew rate in volt per microsecond. You have to divide it by 10 to the power minus 6. So here Vp is equal to slew rate divided by 2 pi f. So the value of Vp, the maximum peak value you can apply to the op amp so that undistorted output will be available. So here the maximum amplitude is calculated with the help of this formula, that is slew rate divided by 2 pi f. The maximum frequency which you can calculate is given by this formula. F max is equal to, so F max is in hertz, so it is equal to slew rate divided by 6.28 into Vm or Vp, it is the same, that is maximum peak amplitude into 10 to the power 6, which is also called as full power response. And full power response, it is the maximum frequency of the large amplitude sine wave with which the op amp can have without distortion. So this is about F max. Now we will go towards the frequency response. So up till now we have treated uh, the gain. The gain of op amp is constant, but the gain is a complex number, and that is a function of frequency. So gain is always a function of frequency, and gain will have specific magnitude as well as phase angle. So this means that the variation in the operating frequency will cause the variation in the gain magnitude and phase angle. So as you are going to vary the frequency, your gain magnitude and phase angle is going to vary. The manner in which the gain of op amp responds to different frequencies is called as frequency response, and the graph of magnitude of gain versus frequency is called as frequency response plot. So the frequency response plot I am showing here. So here the manner in which the magnitude of gain versus frequency is called as frequency response plot. So here the frequency is taken on the x-axis, and voltage gain is taken on the y-axis. So here compensating network. So here generally for the amplifier, uh, as the operating frequency is going to increase, the two effects are more evident. The first is the gain of amplifier decreases. So as the frequency is going to increase, the gain decreases and the phase shift between output and input signal increases. So as frequency is going to increase, the phase shift between output and input is going to increase and gain is going to decrease. So here the manner in which the gain of op-amp changes with the variation in frequency is known as magnitude plot, and the manner in which the phase angle changes with the frequency is known as phase angle plot. So the rate of change of gain as well as rate of change of phase can be changed by using specific components. So rate of change of gain as well as rate of change of phase shift can be changed by using specific components like resistors and capacitors, uh, and with the help of this resistor and capacitor network you are modifying the rate of change of gain and phase shift, and this network of resistor and capacitor component is called as compensating network. So generally first generation op amp are they are going to require external compensating network. So you are attaching the resistors and capacitors outside the op amp in the first generation, but from the latter generation the internal compensating networks, that is whatever the compensating networks are there, they are manufactured or fabricated inside the IC. So this is about your compensating network and the frequency response. So as the open loop voltage gain, so open loop response, so this is the open loop response, this is open loop response, and this is closed loop response. These two are closed loop responses. So here open loop response as well as closed loop response both are going to decrease after the cutoff frequency. Cutoff frequency means here the frequency at which the gain is going to attain the 70.7% of its maximum value, that is your cutoff frequency. So maximum value is this one. When this maximum value reaches to 70.7% of maximum value, then that frequency is cutoff frequency. So after cutoff frequency there is a roll off of 20 dB per decade. Per decade means your frequency is increased 10 times. After increasing the frequency 10 times, your gain is going to decrease by 20 dB. So here in dB 100 to 80, it is going to decrease by 100 to 80 as you are going to increase the frequency 10 times, that is 10 to 100, and 100 to 1k, again there is a 20 dB roll off. So it is constant 20 dB roll off up to unity gain frequency. Up to unity gain frequency, up to this point there is a constant roll off. So open loop voltage gain, it is not a stable voltage gain, and when you apply the negative feedback, then at that time the voltage gain is called as closed loop voltage gain, and it is a stable voltage gain. It is not going to change with temperature or any other factors, but open loop voltage gain is going to change with other factors, and it is not stable voltage gain. So you are applying the negative feedback to make the gain stable. You are applying the negative feedback. So as you are applying the negative feedback, the gain is decreased here. Gain is decreased from this value to 60 dB. Gain is decreased here, and as the gain is decreased, the bandwidth is also increased here. You can see here the bandwidth is increased. So the bandwidth is increased, and the gain, again if you decrease the gain, the bandwidth is going to increase here. So gain bandwidth product is constant. If the gain increases, bandwidth decreases, and if the bandwidth increases, gain decreases. So this is about your frequency response. And the fourth parameter or third parameter, AC parameter, is power supply rejection ratio. So power supply rejection ratio, it is a change in input offset voltage to the change in supply voltage. So if the value is low, then op amp will perform in better fashion. So the value of power supply rejection ratio should be as small as possible. Slew rate is infinite and the frequency response is 1 megahertz for 741 IC. So this is about the AC characteristics. So we will see inverting and non-inverting amplifier in the next session. So thank you.